Lecture 7, Electric and Hybrid Electric Vehicle Components. This is part 1. Today, we're going to introduce you to electric machines. And then next lecture will cover power electronics and battery. In electric powertrain, there are these major components, and in previous lectures we covered internal combustion engine and automatic transmission, but we haven't covered the electrical components, and today we're going to cover that. Let's start with electric machine. The basic structure looks like this. So this is a schematic, and this is real exploded view of a real motor. And you're looking at so there's a stator, that's the housing enclosure, and there is a rotor that's rotating inside of the stator about the axis shaft. And if you look at the actual view, the actual motor used in powertrain, you are looking at rotor with permanent magnets, and then you're looking at stator with coils, and then there's power terminal, and then clutch. And that's how motor looks like physically. And before we talk about more details, we need to talk about taxonomy of electric machines. So usually there are 3 different types of electric machines. First, DC machines, and then AC machines, and then some special drives. And within DC machines, there's permanent magnet DC machine and wound field DC machine. And within wound field, there's series wound, shunt wound, and compound wound. And then for AC machines, there's induction machine, and then there's synchronous machine. And for induction machine, there's squirrel cage and wound rotor. And for synchronous machines, there's salient, cylindrical, and reluctance. For special drives, there's brushless DC motor, switched reluctance motor, and linear motor. Okay. And this is this table shows quick review of their characteristics of different types of electric motors. First, starting with AC motors, there's 3-phase, and there's single phase, there's induction, synchronous, again induction and synchronous. And depending on the power range, different applications use different types of AC motors because of their cost, their size, their efficiency, and so forth. For induction, there's squirrel cage and wound field, like we mentioned earlier. And then synchronous, there's a permanent magnet and DC field windings, and so forth. So please take a look for more detailed information. And let's look at one by one. Okay, so this is DC machines, principles of DC machines. this is how it's structured. The key here is that you have this brush that changes the direction of the current flow within the windings. Okay, so you have field winding or permanent magnet at the stator. So if you can generate this field either using permanent magnet or using windings and flow current within these windings, then you're going to generate this field, magnetic field. And within that field, you are going to what we need to do to rotate or generate torque within the rotor is that we have this windings. These are windings, and you flow current through these windings, and you're going to also generate a field within the rotor. And if you generate a field that's also north here and south here, then they're going to repel, right? So they're going to push, and then it's going to generate torque. And the trick here is that when it starts to rotate, when it's rotating, you need to change the direction of the current flow. Otherwise, this north and south, this field is going to rotate. If you fix the field of the rotor, then this north will now attracted to south of the stator, and this south of the rotor will be attracted to north of the stator and will stick there, right? And will not generate torque anymore. So to continuously produce torque and make rotor rotate, you need to continuously change the direction of the current flow with respect to the rotor. Or you should continuously generate field that generates torque with respect to the stator. I hope that's clear. Okay. So this is an example illustrating how DC machines actually alternate this current flow and generate field, and torque is illustrated here. So let's say there is this magnetic field that's generated by the stator, and within that field, if you make so this is a rotor winding, and then here's a brush, and here is some DC power source, and because they are touching here, it's going to produce current flow through the winding, and it's going to generate a field within the rotor, and that generates torque, and it's going to start rotating. So this figure shows it rotated about 90 degree, and once it passes that 90 degree, this connection is now disconnected. Okay, because here there's this empty space here, right? So now, but there is inertia that wants to continue to rotate, so it's going to now touch this metal part, and this metal part, and now the voltage applied to this winding is switched. The direction now switches. So initially, it was flowing B to C, but now the current is flowing C to B, right? So, and you're looking at the alternating voltage across this A and D are showing here. So this is from source perspective, but from this winding or rotor perspective, voltage applied is now switching, and that's because it's rotating. Okay, so now what's happening here is that you're actually generating alternating current within the rotor. Okay, by doing so, you can continue to generate torque and generate the rotating motions. Okay, so that's how it's done in DC machines, and let's take a look at AC machines. For AC machines, the main difference between DC versus AC machine is that your power source is alternating your voltage. So you don't have to, maybe if we design this properly, we don't have to have this alternating device, which is this brush mechanism. Okay, so basically that's the key difference between DC versus AC machines. But because you don't have that brush, here the alternating frequency was automatically adjusted by the speed of the rotor. But here you need to properly control that. Okay, and you're looking at 2-pole versus 4-pole AC machines. Let's say you have a stator that has this field, north, south, 4-pole, and then within the rotor you are going to generate a field that creates this torque, magnetic field, using current flow, right? So to explain that better, this should be a good illustration of that. So this is a three-phase AC machine. How three-phase AC machines work. The trick here is that by generating, by creating these three-phase induced current flow, you can actually rotate resulting field that's rotating. So this, you're looking at it from resulting final combination of three-phase induced magnetic field. So here, your magnetic field is changing with respect to phase A, phase B, phase C. But if you think about it, because the winding is not moving, right? Instead, the current is alternating. So what's going on here is that what you can do using alternating current, you can change the field in one direction. In the case of this phase A, left and right, and phase B, you put the winding a different orientation, and you are going to have this type of alternating field, magnetic field. And you put another phase that's 120 degrees offset from other two, and you're generating another alternating magnetic field. And what this resultant is showing is that summation of these three is this resultant field. And you can see that the resultant field is that it's rotating. Okay, so what's in other words, what's happening here is that you're creating this rotating field by using alternating current, but you do need, in order to create this smooth rotating motion, rotating field, you need three-phase or windings that have different orientations, different positions, and then have different phase. Okay. Right. What's going on? So let's take a look at different types of AC machines or electric machines in general. This table compares different types of electric machines and gives you some scores on different criteria. And we're looking at DC machine and induction machines and permanent magnet machines and synchronous reluctance motor. And for characteristics, we're looking at power density, efficiency, controllability, reliability, technological maturity, cost, and so forth. So looking at these scores, you can see that DC machines have relatively low power density and efficiency, but have good controllability and technological maturity. Induction machines have very good controllability, reliability, and cost, and so forth, but relatively weak power density and efficiency. But if you use permanent magnet PA machines, can give you higher power density and efficiency, but its controllability, reliability, cost is somewhat lower than induction machines. And for electric vehicles, most of the time AC machines are used, and usually induction machine and permanent magnet synchronous machines are used. PM is good for high power density and efficiency, and induction machine is good for cost. Okay. So DC machine, we briefly explained, introduced you how it operates. So this is the brush, and as it rotates, the brush touches different windings, and that creates alternating magnetic field and continuous torque. And usually the motor map looks something like this. So you have constant torque and then constant power region. And these are some of the characteristics. Same problem again. And then induction motors is actually quite cheap, reliable, because it doesn't require permanent magnet. Usually permanent magnet is requires rare earth material, which is usually expensive. So, but in the case of induction motors, you're generating the field using windings and current through these windings. So I'm sorry, for rotor, so for induction motors, you have field windings at the stator, and for rotor, if you use squirrel cage, you do not have windings, but you just need a cage looking rotor, and then there's it's called induction motor because you're inducing magnetic field within the squirrel cage, which is the rotor. Okay, so it's very simple, design and mechanism. So that's why it's cheap, but it's not that the power density and efficiency is not great, but it's cheap and reliable. So you're looking at the field generated by the stator is rotating, and the rotor is rotating, and as you can see, the field from the rotor perspective is fixed, but from the stator it's rotating. Okay, so you need to rotate the field for the stator continuously rotating along with the rotor, so that you can continue to generate torque. So, and you are also looking at the motor map here, constant torque, constant power, and then there's flux weakening region. Next electric machine is PM synchronous motors. And this one uses permanent magnets. So this red and green part in the rotor has permanent magnet. So So you already have field within the rotor itself, and all you have to do is rotate field for the stator, and that's exactly what's happening here. But you need that rare earth material for permanent magnets, and it provides good power density because you have strong magnetic field within the rotor. But the cost is high because of the permanent magnet, and you need to control the field so that it's synchronized with the rotor speed. Otherwise, your torque and speed, may not be, it may not track the desired torque or speed. This is another more realistic example of PM synchronous motors. So they put this permanent magnet here within the rotor to generate magnetic field within the rotor, and then you have these windings at the stator. Okay, you have windings at the stator, and you flow currents, alternating currents, and by applying the three-phase phase, you can rotate your magnetic field continuously and smooth. Okay. This is switched reluctance motor. We're not going to talk a lot about this because usually this is not used for electric vehicles, okay? But take a look. So far we looked at how electric machines, the motor map, torque and power map of electric machines look like, and let's compare that with internal combustion engines. Okay, I briefly mentioned about this in the earlier lectures, and if you see, the characteristics are quite different. If you look at the engine, the torque is relatively flat. In fact, torque is lower towards the low speed region. But for electric machine, the torque is higher actually in the low speed region, and later on the torque diminishes with increasing speed, and this is called constant power region, and this is constant torque region. And in fact, this is one of the nice characteristics of electric machines have. And what this means is you can generate high torque for low speed, and you reach this maximum power quite fast. And then, so whereas for internal combustion engines, if you want maximum power, you have to operate at high speed, right? And for most of the region, your power is lacking. So the engine, even if the engine can produce maximum of 100 kilowatt, at low speed you just cannot produce that power, full potential. But electric machines can actually provide all of that power from low mid speed. Okay, approaches that max power fast, and that leads to no need for transmission. If because one of the main role and need for transmission was to to amplify torque in low speed regions, right? Because the torque line was relatively flat. So as a power source, mechanical power source, electric machine is close to ideal, meaning that we can't do anything about power, from energy conservation law, right? But torque and speed, so if you draw a constant power line, this is your, for a given power, this is the maximum ideal torque we want, right? For a given motor, whether it's an engine or machine, electric machine. But the engine looks, if you think about it, engine is looking something like this. Okay, so you have a lot of losses here. You're not fully generating all the torque and power for this region, but for motor, you are actually generating all the full power except for this region. Okay, but that's not bad, compared to engine. So that's why you do not really need transmission, because if you let's say we add transmission for electric machine, and what's going to happen? What's going to happen is that you're going to shift maximum speed and max torque, but not power. Okay, because again, power equals to torque and speed. So if you use transmission, multi-speed transmission, and use different gear ratio, you might be able to increase torque, but you cannot increase power, right? Energy conservation law. So if you amplify torque, then what's going to happen to the speed is maximum speed will reduce. Or if you use higher speed, and if you increase maximum speed of the motor, then your torque, maximum torque will drop. Okay, so that's what's going to happen if you apply transmission for electric machines. Okay. So if you combine engine with a motor, then you get something interesting, torque and power line. So this is an example for I think Honda Accord, and engine has this flat, or higher torque towards high speed, maximum torque line, and if you add electric motor on top of that, which looks like this, right, then you will end up with maximum torque line something like this. So this is engine plus motor, maximum torque line. But of course, you will drain battery energy if you apply maximum power. If you ask for maximum power from both engine and the motor. Okay, so this is nice because you can get higher torque and higher power at low speed. Okay, so that also helps. That's also a nice feature for hybrids. Right. Okay. Let's see. So let's move on to operation modes. What this shows is that how motor operates from mechanical and electrical perspective. This is a this plot is on a showing this operation in 4 quadrants on a torque speed plot. And for positive speed and positive torque, it's called motoring mode. And for negative torque and negative speed, it's also motoring. But if speed is negative and torque is positive, then the motor is working as a generator. And if you have negative torque and positive speed, it's also a generator. And this has to do with torque and speed and voltage and current, assuming perfect 100% efficiency. Okay. So using this equation, you can see what's going on between mechanical power versus electrical power. So let's start with the first quadrant. So let's say in the case of motoring, so motor is rotating at the positive direction, positive speed, and the torque is also applied towards that positive direction. And in that case, power is positive, obviously, right? And to in this operating modes, this quadrant, what happens in the electrical circuit is that you're applying actually positive voltage, and the current is also positive. So your current is flowing this direction from electric machine perspective, and from electrical perspective, this is also positive direction. But let's say your torque is now negative and the rotating speed was positive, then negative torque, positive speed, then motoring, you're generating. So the motor was rotating at the positive speed, but the torque was negative, so the motor speed starts to decrease, and that's generating, right? And what happens to the electrical circuit is that you're applying positive voltage, but the current is flowing negative direction, and that leads to negative power flow, and that's generating. So you're converting, so in the generator modes, you're converting mechanical power into electrical power, okay? Negative power flow. Assuming positive power flow is that electrical power is converted to mechanical power. And you can repeat the same process and take a look at how mechanical and electrical aspects of the power flow and voltage, current, speed, torque changes in this 4 quadrants. So to be able to operate within the 4 quadrants, all 4 operating modes, you need to be able to change the voltage and current. So if you can apply positive voltage and positive current, then your motor can only do motoring. But if you want to be able to do all of this, all 4 modes, then your voltage, current should be able to cover the negative values, which is related to with both hardware and software. And the speed also needs to be able to be able to rotate in the negative direction. Okay. So this has to do with mechanical side, whereas negative torque is controlled by the electrical side. Okay, the negative current. Electric machines electric machines are not perfect, meaning that it has losses and efficiency. So this is a quick loss diagram, loss chart. So if you have, let's say we are doing motoring, meaning that input is electrical power and output is the mechanical power. And when you apply voltage and current to the motor, then you have these electrical losses, copper loss, eddy current loss, hysteresis loss. So that's happening within the electrical circuits. And then you also have this mechanical losses, which is friction loss and windage loss. Windage loss is more of it's also called viscous loss from, spin, more aerodynamic drag type of things. So when it comes to efficiency, you need to be able to model this or measure these and then compute the efficiency. But usually what is done is that you measure the input and output in the test bench, and you compute for efficiency and losses. Okay, if you know these input and output values, then you can compute these losses, right? I'm sorry, these are not losses. These are losses, right? So, but one thing that can be tricky for electric machines when it comes to computing efficiency or computing losses is that you need to be careful with the sign of the power or direction of the power flow. What that means is that if you have a motor and your input was electrical power and output was mechanical power, then this is the definition of the motor, and which is this. But if you have, if you're operating in the second and fourth quadrant, works as a generator, then they need to be switched, meaning that mechanical power is the denominator and electrical power is the numerator. And you can do this by applying, -1 power of this value. So you can inverse this function, right? So usually when it comes to modeling, you need to do this properly. Otherwise, you can have efficiency that's higher than 1, okay? Which is physically impossible. And this is an example of steady-state efficiency map. So you run the motor at different speed and different torque region. You probably have like a grid, and at different operating speed, operating torque at steady state, you can compute how much energy input is consumed and how much output torque is generated by the motor. And then you can compute the efficiency and the losses. So if this is an example of that, and you can see that sweet spot is somewhere here. But also note that when you change voltage, this efficiency map also changes. Okay, so if you can control the voltage, then you can also improve or optimize or control voltage to improve efficiency. Okay, I will stop here, and I will continue from here next week. Okay, so again, we will meet next Tuesday. Please post your questions by Monday, 4 p.m. And we'll have discussion sessions on Tuesday, and we'll talk about those questions. Okay. Thank you for your attention, and have a good weekend. Bye-bye.